The idea of limits and continuity for function of more than one variable really closely relates what we've always come to love and adore when we're talking about functions of one variable. So let's start off with a definition. Definition of the limit of a function of two variables. So let f be a function of two variables whose domain D includes points arbitrarily close to AB. Then the limit as xy approaches AB of f of xy equals L. What this means is that if for every epsilon greater than 0, this is the extension of the epsilon delta definition, there exists delta greater than 0 such that if xy is in D and 0 is less than the square root of x minus a squared plus y minus b squared, which is less than delta, then the absolute value of f of xy minus L will be less than epsilon. Now, what we want to do is we want to think of D as really just simply being a disk. This is some region about the point AB. So really all this is saying is that when I'm in some region about AB, when I'm taking the limit as the function approaches, or as x and y approaches AB, when I'm in some region about AB such that decides this region is less than delta, then I'm going to be within epsilon of the limiting value. This is very much like the definition of a limit for a function in one variable. Now, very commonly, we'll write this with x approaches a and y approaches b rather than like this, because clearly if we start getting around into x, y, z's, and t's and so forth, this can get kind of crazy to keep up with. And likewise, this can kind of stack up and get a little bit crazy too. So we can really use vector notation if we need to here. But these two are very common notation for the limit of functions in two variables. Now, notice here that this radical we did, the square root of x minus a squared plus y minus b squared, is really just the distance between xy and AB. Now, since we're working in 3 space, being within delta of AB suggests that we have a disk about AD with a radius less than delta. So commonly this D was subscript with D sub delta, simply indicating that it's a disk and the radius is less than delta. Now compare this definition to the definition of a function of a single variable. Now this definition simply says that the limit as x approaches a of f of x equals L. What this means is that for every epsilon greater than 0, there exists delta greater than 0 such that if if x minus a is less than delta, so I'm within delta of a, then the absolute value of f of x minus L is less than epsilon. It simply means that when I get within delta of A, then I will be within epsilon of L. So this is almost identical to what we did with the function of two variables. It's just that we took in consideration both variables rather than one. Now, for the limit to exist, we needed to show that the left-hand limit is actually equal to the right-hand limit, which equals to L, some real number. What that means graphically is if this is A, and here's a limit at L, then as I approach A from the left, and I approach A from the right, the left and right hand limit, they both approach the same value of y, which is in fact L. Now, for the limit to exist, I don't have to have that point defined. I could have a hole there, and the limit would actually still exist. Essentially, all this definition is saying is that when I get really, really close to A on the x-axis, I'm going to get really very, very, very close to L on the y-axis. And in two space, we have to consider what happens from both directions. We can't just consider what happens as I approach A only from the left or only from the right. Both directions must be taken into account. And the reason for that, obviously, just as a reminder, is we could have something like this going on. And this is A. Where as I approach from the left, I have one value, call it L1. And as I approach from the right, I have another value that I'm approaching, call it L2. In this case, obviously, the limit won't exist. That's why I have to check from both directions here to confirm that the limit really does exist. Now, carrying this idea over to 3 space, for f of xy, we have a surface, not just a line. And as such, the distance from the point AB can be represented as the square root of x minus a squared plus y minus b squared. So what that's saying is that I can represent this as my distance d equals x minus a squared plus y minus b squared. Well, that would then imply that d squared equals x minus a squared plus y minus b squared, which for fixed values of d, we actually get concentric circles. So what that means is, unlike in 2 space, which requires to only check the value of the limit is L, check to see if it's L from both directions. In other words, back to this idea, if this is A, and here's my function, I need to check from both directions to make sure that the limit really is L. But in 3 space, because this is actually the equation of a circle centered at AB with radius D, I have to check from an infinite number of directions. Because in 3 space, what my function or my graph's going to look like, I may end up with something like this. So I have this surface perhaps up here. I'm just kind of make a patch here. Here's my surface. And bring my axes out. And down here, I'm going to have, let's say this is my x-axis, y-axis, z-axis. So down here someplace, I'm going to have a point AB. And I need to figure out what the function's doing. Perhaps the value of the function is like right here. So say this is on this surface up here. So what I need to do is I have to figure out what's happening as I approach AB from really an infinite number of directions. So as xy gets really close to AB, what's happening here on the function? What's happening to z? So because this exists on a plane, the point AB, as xy gets closer and closer to it, which gives me this z value, there's actually an infinite number of directions that I can approach this thing. And they all must equal L for the limit to exist. So when we are within epsilon of L, in other words, we've got L plus or minus epsilon, we are actually on a disk, like I said earlier, denoted d sub delta, with a radius which is going to be less than delta, centered at AB. So perhaps I have this disk right here, and obviously delta gets infinitely small, so this disk collapses on it. But what I need is to figure out what's going on at every point literally within this disk, or every possible lane of approach from within that disk. So what I'm thinking here is that this value on the z-axis, this is my L. So when I get down here, when I get within delta of AB, what this is saying is that this is minus epsilon. Well, actually it's L minus epsilon. This is L plus epsilon, that I'm getting within epsilon of L. So you can see this is very, very, very much like what's going on in 2 space. So in our situation here, we can actually say, so F maps all values within delta of AB, of course, except possibly actually at AB, onto the interval L plus or minus epsilon.